Here we're going to take a look at what the extrema of the graph of a function are. So basically, in a nutshell, whenever we're referring to extrema of the graph of a function, really what we're referring to is high points and low points in the graph of a function. Okay, so you'll see that I just did underline a couple of terms right there. One of them is extrema, which is actually just the plural version of the word extremum, which would be the singular version of the word. So ultimately, when we define what an extremum is, we're really just referring to high or low points in the graph of a function. So really, you're just kind of looking for maximum points, right? Like top of a mountain, and you're looking for minimum points. So like the bottom of a valley, per se, right? So one thing that can kind of allow us to maybe more mathematically define extrema is to refer to turning points of the graph of a function. So when we have this term turning point right here, what defines a turning point is that it has to be a point on the graph of a function where the function is going to either, number one, it's going to change, and it's going to change from increasing to decreasing at that point. Or our other option is just vice versa, to change from decreasing on an interval to increasing at that particular point. And that's how we're going to classify a turning point. So looking at this very first picture right here, you'll see that the function increases on that green interval, and then on this red interval right here, it's decreasing, and then the function starts increasing again on that green interval, right? So at this particular blue point right there, and this particular blue point right there, those are classified as turning points because they're the points on the graph of the function where the function changes between increasing and decreasing. So whenever we do have turning points, actually, those turning points end up being extrema of the graph of the function, right? So in the cases where it goes from increasing to decreasing, those are always higher points, and so we can refer to that point right there as being a maximum in the graph. And then whenever it changes from decreasing to increasing, those will always be lower points in the graph of the function, and we can refer to that as being a minimum. Now, you can call them maximum and minimum, even if they are not the highest nor the lowest in the graph of the function. So you could have a function that has like 11 different minimums, right? But they might be at varying different heights. So it doesn't matter if it's the lowest or not. We can all call them sort of like minimums in the graph of the function. And the same thing is true for maximum points. In a little bit, we'll distinguish between the highest and other high points using certain terminology, and then the same thing for the lowest and the lows and how we can separate those things from each other. But before we get there, just one last thing right here to recognize that in the graph of this function that I just highlighted in green right there, we get to that little point right there in the middle, right? And the graph does flatten out, but only at that particular point. And then if we continue following the graph on the other side of that point, the graph of the function still keeps increasing. So at that particular point, right here in the blue, it is not changing between increasing and decreasing, right? It kept on increasing. So this point right here is not a turning point in the graph of that function. So it's not going to end up being an extremum in the graph, right? It's not a minimum. It's not a maximum. Okay. So it does have another name, but we don't need to get into that quite yet. So just recognize that those sorts of points are not going to be any extreme points in the graph of a function. All right, so what I was just alluding to a little bit ago is how we can separate between the highest and other high points, and then also separate between the lowest and other low points. So when you're looking at a graph of a function and we're looking for extremum, and we call them relative extremum, what that means is that they're going to be extreme points in a relative area of the graph, right? So literally any high or low point can be a relative extremum. So the ones that are not the highest and the ones that are not the lowest are relative, and then also the one that is the highest is still a relative extremum, and the one that is the lowest is still a relative extremum. Because in those areas of the graph, the highest point is going to be a high point in that area of the graph, and same thing for the low point. So any high points, any low points are always relative extremum, okay? So the absolute extremum means it absolutely is the most extreme point, right? So it means it needs to be the highest or it needs to be the lowest to be. Okay. Now sometimes there's ties, right? So there might be 2 or 100 points that are all the same height. Okay, and they all are the highest, and that's okay. So you could call all 2 or all 100 of them the absolute if there's a tie, right? And same thing is true for the lowest. Some other words that we will also sometimes use is instead of this word relative right here, we might refer to it as being a local extremum, meaning in that local area of the graph, it's a high point or a low point, okay? And then another word that we might use instead of the word absolute is the word global in front of an extremum, just basically saying that in the entire like globe or world of the graph, it's the highest. Okay, so get used to seeing and using those terms as well, local and global instead of relative and absolute. Okay. All right, so in a couple examples right here, we're just asked to identify the relative and the absolute extrema of the graph of each function. So this first graph right here doesn't actually have any xy coordinates labeled or anything. So what I'm really just going to do right here is I'm just going to put some blue dots at the high and low points of the graph of this function. So it does turn out that there's 5 total extrema. What that means is that there's actually 5 total relative extrema. So if I call this right here point A, point B, point C, point D, and point E, right? So if we were to try to identify any relative maximum points, the relative maximum points are going to be all of the different high points you're going to find. So it turns out that points A, C, and point E are all relative maximum points in the graph of that function. And then for any relative minimum points in the graph of this function, these low points right here, point B and then point D, sorry about that, those are going to be relative minimum points. Then if we were looking for absolute extrema, the absolute maximum would have to be the highest point if there is one on the graph. And it does turn out that if we look at all of the relative maximums of A, C, and E, that this point right here would be the highest. So the absolute maximum occurs at the point A in that graph. And then for any absolute minimums, we actually do have a lowest point. B is a little bit lower than where D is at, so therefore we can refer to the absolute minimum of the graph of that function being at point B. Okay? And then just for this example right here, of course it's going to be pretty much very similar, except this time there's actually like ordered pairs labeled based on where these high points are and then also where these low points are, okay? So when you label any relative maximum points, you can just give the coordinates of the points. So this point right here and then this point right here would be relative maximum. So you can label negative 2.355, 3.798 is one of the maximum points. The other one is 1.169, 1.658, right? For relative minima, you have a couple. You have one that's occurring right there at negative 0.526 and negative 0.47. The other one that you have occurring right there is at 3.312, negative 5.425. Then if you're looking for any absolute extrema, let's say we're looking for an absolute maximum. So we'd want to look for the highest point. So it looks like, this one's the higher of the two maximums, but actually there are points that are higher on this graph because we can find, like up here, even higher points. And even if there was an arrow right there, then actually there isn't going to be a highest point at all because the graph will keep going on forever and ever and ever. So if we do assume that there's an arrow there, there's actually no absolute maximum in the graph of the function. We would not be able to find a point that is the highest. Okay, so there will be graphs that may not have a highest point, right? So you wouldn't be able to specify one. Similarly, if we were to assume that the arrow is also on this side of the graph, then it's going on forever. And so there's going to be cases as well where you could not have an absolute minimum existing. And so that would also be the case with this graph. Okay. There are sometimes graphs where maybe you will have an absolute maximum, but no absolute minimum, right? So you could probably like think like, okay, so let's say that I have this graph right here, right? So it would have an absolute maximum because you would be able to find a highest point, but because both arrows point down, it wouldn't have an absolute minimum, right? So you kind of flip that graph upside down, you just get the flip of that where there would be an absolute minimum, but no absolute maximum, of course.